Persona 5 walked so Persona 3 Reload could run with improved character models, stylistic lighting, ray tracing, and of course, its beautiful user interface and VFX. Like, just look at this. Each individual menu is a piece of art to be admired, which has me wondering, how much of this is artist-authored, how much credit goes to graphics programming, and lastly, how could we make it all ourselves? Just like last time with Lethal Company, we'll be using NVIDIA Insight to analyze every aspect of Persona 3's rendering from start to finish. Typically, the user interface is drawn last, so let's do a general overview of the game's rendering up to when the UI would be drawn. Obviously, Persona 3 isn't seeking to be a realistic game, so we refer to its visuals as non-photorealistic rendering instead of physically based rendering. But just because Persona 3 isn't physically based doesn't mean it isn't following its principles. In fact, most of the time, NPR is underneath the umbrella of PBR because it's no different than stylized art in other mediums. As an illustrator or painter, you learn to draw from reality first in order to learn the rules everything abides by, as well as develop an understanding of anatomy and where things should generally go. Only after you've learned the rules can you properly break them and simplify to your desired level of stylization. It's the same with non-photorealistic rendering. Stuff like toon shading is usually a simplification of physically based rendering. These techniques are invented by those who know the rules and how to break them to get desired results. With that in mind, let's take a look at the game. But first, something a little different. This video has been sponsored by Brilliant. Brilliant is the best way to learn math, data science, and computer science interactively. Brilliant offers thousands of lessons from basic to advanced, so if you're just getting started learning math or are brushing up on your linear algebra for graphics programming, Brilliant has something for you. Even if you don't know where to start, that's no problem. Brilliant customizes its content to fit what you need. Just take a quick quiz when you sign up, and Brilliant will match you with lessons that fit your interests and your level of expertise. I personally use Brilliant whenever I need a quick and accessible refresher on math concepts I haven't worked with in a while, such as complex numbers or some aspect of calculus. I appreciate that Brilliant makes it easy to find lessons on topics I'm looking for. Be sure to try out everything Brilliant has to offer with a free 30-day trial and 20% off an annual plan when you visit brilliant.org/Acerola or click the link in the description. Thanks so much to Brilliant for sponsoring this video. Here in the dorm room, we walk underneath a light source to see how the light interacts with the protagonist. Immediately, you can tell the difference the light source makes compared to when the protagonist is only in ambient light. It also clearly shows us which details are mostly artist-authored and which are driven by shaders. In physically based rendering, all of the detail comes from lighting calculations in the shader because that's how the real world works. We see things because light bounced off of it and into our eyes. We use the normal vector, a vector orthogonal to the surface at any given point, to determine how lit a pixel should be, which is where shadows and thus detail comes from. These normals are stored in each pixel of something called a normal map, which is a texture that gives us highly detailed 3D models by allowing the lighting calculations to operate per pixel instead of per vertex. This is combined with something called an albedo map, which stores the color information of a 3D model without regard to any sort of shading. We take the direction of the light source and the normal vector, calculate the dot product, and then multiply it with the albedo to get the diffuse lighting, which is added to the ambient light. The dot product is like an exposure value for the albedo. A dot product of 0 reduces the resulting color to black, meaning in that case, the pixel was facing away from the light source and was thus in shadow. I have a shader here that does exactly that given these two textures. You can see that the parts of the sphere pointing away from the light are shaded, and on a per pixel level, the normal map drives all of the finer details. While this is cool and physically correct, it also looks very harsh and ugly. The solution is to add more lights because, again, that's how it works in the real world. But having all these details dependent on the position and direction of existing light sources can be frustrating, and the more light sources you add, the more expensive everything gets. This is where Persona 3 breaks the rules. Details like clothing wrinkles are not driven by some complex normal map, but rather just painted onto the character so that they are always present and are unaffected by poor light conditions. We can see the clothing wrinkle shadows don't change when the protagonist is under the light. Instead, the light source serves to cast physical shadows and brighten the character where the light hits. Persona 3 makes use of another PBR concept known as fresnel, which is where this slight rim lighting comes from. Fresnel is something you observe every day. It is the phenomenon in which the strength of a reflection is dependent on the viewing angle. This is easily observed with water. When you're at a lake and you look straight down at the water, you can see through it just fine. But very quickly as you go towards the horizon, the water surface becomes more mirror-like as the strength of the reflection increases towards the grazing angles. It is also observed in hallways with shiny floors, or right here on the protagonist's shoulders and hair where the angle of incidence is greatest. You can see that the reflection on the shoulders disappears when you look down at them. Other than that, there isn't much else the lights in Persona 3 Reload are doing, but we've still got more to look at. The game has very nice edges on its character models. These aren't painted on like the clothing wrinkles because you can see the edges change dynamically with the animations, so there's some sort of edge detection shader technique at play. We also have a very tasteful amount of bloom, which is responsible for the light looking so soft. Then there's this weird sort of line effect on shadows. Whether or not this is an intentional comic book-like effect or a shader artifact is unknown. Lastly, we have ray tracing. If you have terrible frame drops while playing this game, it's because you don't have a 20 series or better GPU with ray tracing hardware, and should disable reflections in the graphics settings. If you disable reflections, the game swaps to screen space reflections instead of ray traced. The difference in quality is very obvious in the Tartarus lobby though. With ray tracing enabled, the reflection of the clock is always visible regardless of camera angle, whereas with the shitty screen space reflections, the clock gets cut off once it's no longer on screen. But you can tell that this area was designed for screen space reflections. The default camera view is very conveniently placed such that you can't see the clock cutoff. This means the ray tracing was probably an afterthought in the design process, which is unfortunate. Now that we have a general idea of what's going on, let's hop into the frame capture to see how it all gets put together. Let's start by taking a capture here in the protagonist's room where we can get close to the camera. There's actually a graphics bug in view, but I'll point it out later. Unlike Lethal Company, Persona 3 Reload is made with Unreal Engine and is also a AAA production, so we can expect a more sophisticated and concise render. Unfortunately, because it's a AAA production, a lot of information is absent, like the names of the shaders and textures. That information is what made it really easy to tell what was going on with Lethal Company, but without it, I have to try a bit harder with my eyes to decipher the techniques at play instead of taking the easy route with metadata. This frame capture contains 7,612 events and starts out with something called a Z prepass. A Z prepass, also known as a depth prepass, is a common graphics programming technique used to avoid something known as overdraw. Overdraw is what happens when a pixel gets written to multiple times during a frame render. Imagine we drew a rectangle that covers the screen. That's all well and good, but now imagine we drew another rectangle on top of it for some reason. We'd now have one full instance of overdraw and wasted all of that work we did to draw the first rectangle because we can't see it anymore. This doesn't sound like that big of a deal until you run some numbers. A 1920 by 1080 monitor contains a little over 2 million pixels. So we wasted 2 million instances of our shader. You can then imagine why it would be very unoptimal to do some complex calculations like ray tracing, only to throw it away and do it again on top of it. When that first instance of work is already costing you a lot of your performance budget, any bit of overdraw could be enough to end your career. A number of solutions exist, such as deferred rendering, which I explained in the Lethal Company video, draws all of the objects on screen and then does the complex lighting calculations as a post-processing effect, ensuring that there is no overdraw. Another solution is the Z prepass, where we draw all of the objects in view to the depth buffer first, allowing shaders to stop what they're doing if the pixel they are about to write to is behind the pixel that already exists in the depth buffer, avoiding the complex calculations and saving you from wasting work at the cost of doubling up on your vertex shaders. Persona 3 Reload chooses the route of the Z prepass, which must have you wondering, if deferred rendering is a solution to overdraw, and Persona 3 is using a different solution, does that mean Persona 3 is making use of forward rendering instead of deferred? Persona 3 is forward rendered, meaning it does all of its light calculations immediately when the object is drawn. But we still have to do one thing before the lighting stage can execute. The next stage of Persona 3's rendering is a technique known as shadow mapping. You might not have ever thought about it before, but shadows are often the most expensive part of a render pipeline. It's a very non-trivial problem, and there's a reason a lot of older games have completely fake shadows. But Acerola, couldn't you just look at the pixel's point in space and then draw a line between that point and the light source to see if there are any objects in between that the line collides with, thus casting a shadow on that pixel? Yeah, you could do that. That's called ray tracing. Hopefully this demonstrates how intuitive, convenient, conceptually simple, and absolutely accurate ray tracing is for just one of its many use cases. But unfortunately, ray tracing is expensive. So we have to devise another solution. Since we want to know if another object is in between the light source and the pixel we are drawing, but we are unable to actually know about all of the objects around the pixel, then we have to do it cleverly with texture data. If we do the same thing as the Z prepass from earlier, but from the perspective of the light source instead of the camera, we can write the distance of each object from the light source to something called a shadow map. Then, when we're rendering a pixel, we check if it's behind an object in the shadow map, and if it is, it's in shadow. This method, while clever, has many drawbacks. For instance, we need to do this shadow mapping process for every single light source that we want to be able to cast shadows, which gets extremely expensive the more complex your scenes are. This is why foliage in video games never cast shadows really, because imagine how expensive it would be to render all of your grass multiple times for every light source. It's just not possible. Another issue is that the quality of our shadows is limited by the texture resolution of the shadow maps. The higher resolution they are, the more accurate the shadow information, and the better the shadows look. But the memory cost and bandwidth quickly becomes a bottleneck. Despite these problems, shadow mapping is used by pretty much every game because it's cheaper than ray tracing, and the only alternative is just faking your shadows with a mesh or the infamous circle drop shadow. You can see Persona 3 Reload filling in its shadow maps here to prepare for the forward lighting pass. For whatever reason, it wastes time rendering a shadow map for the light that's in the hallway on the other side of the door. This is probably a bug, but it barely renders anything at all, so it doesn't matter that much. With the shadow mapping finished, the lighting stage is ready to execute. Like I said earlier, Persona 3 is forward rendered, so lighting is done at the same time the object is drawn. In the last video, I mentioned that in the real world, games are usually a weird combo of forward and deferred, which is true here as well. Persona 3 is writing out a lot more information than just lighting results for future effects. Unfortunately, it's kind of impossible to know what this data represents without extensive investigation, but the obvious stuff is the normals, which we can see are very simple and serve to accentuate the overall shape of the model instead of juice out more detail. Also, because of the Z prepass, we don't have to worry about wasting work on pixels that are behind other pixels. The edges of the protagonist are drawn before anything else. We can see that there is a whole 3D model here for these edges, so Persona 3 must be using some variant of the inverse hole technique, which is where you discard pixels that are facing towards the camera, so the edges are only drawn on borders, and the player model underneath is still visible. There is a discard instruction in the shader assembly, so it's certainly doing something in that ballpark, but how exactly the discard is determined is buried underneath a lot of logic. After that, it's business as usual. Every object in view is drawn with lighting, but you'll notice there aren't any cast shadows. This means we're looking at the diffuse light only right now, and they decided they want to do shadows later. After all the objects have been drawn, the game draws the player again into a mask so that presumably future effects can operate on only the player or on everything except the player. Since the base lighting is done and all the objects have been drawn, we move on to post-processing. The first post-processing effects are going to be those that mess with the lighting of the scene because it's making adjustments to what exists physically in space. Generally, this means effects like screen space global illumination or screen space ambient occlusion, which Persona 3 Reload is doing here. In this case, it is ambient occlusion. Persona 3 is approximating the absence of ambient light in places where light would be hard to reach. Despite being used for realism in games quite often, it is actually not realistic in the slightest, which is why it works great for our stylized games. game. We can also see a very strange pattern to the ambient occlusion, which looks suspiciously similar to that weird line pattern we saw earlier in our visual study. We'll know why it looks like this when we learn how we approximate ambient occlusion to begin with. For each pixel, we want to do a number of samples in a hemisphere around that point in space to check how many samples intersect with another object in the depth buffer. If there are a lot of intersecting points, then that means it's probably hard for light to get to that spot, so it's probably going to be a little darker. While the logic is admittedly simple, the results are pretty nice. The more samples you do, the more you get a perfect approximation. If this confuses you, please take a moment to review integral calculus and then come back. Unfortunately, it's very expensive to do even a small amount of samples, so you want to try as hard as you can to get a decent distribution of directions in your small sample pool for a better approximation. Generally, this means your distribution is uniformly random, and so the result is visibly noisy. This is then usually solved with something like a basic denoiser, or if you combine it with temporal anti-aliasing, you get perfect denoising for free. Persona 3 doesn't use random numbers for their SSAO, they use dither noise, which is why we see a dither pattern in the ambient term. This is because the developers know the noise is going to be visible no matter what, and having white noise on the characters would be ugly, so they opted to go with the stylized dither noise to turn what would normally be a con of SSAO into a pro, and adding a little spice to the visuals of the game. The SSAO gets multiplied with the additive lighting buffer to add more interesting shading, and the frame continues on. Next up is the hard shadows. Persona 3 uses the shadow maps of each light source we made earlier to create a shadow mask for the scene. There's one pass for each light source, but there's only two lights, the sun outside and the light in the room. It's interesting to note that the game creates these shadows with inverted shading logic. Instead of darkening the areas in shadow, everything that isn't in the shadow mask gets brighter, giving the scene its much needed brightness adjustments instead of making everything even darker, except for these window spots. That's not the only thing that's going to brighten up the room though, as the next portion of the frame uses ray tracing for indirect lighting, which gives us global illumination and reflections on the glossy surfaces. Most people would probably never notice that the bedstand and laptop screen are reflective. For some reason, the wood material is reflective as well. These reflections are composited with the lighting buffer, and the scene is further illuminated, giving us pretty much the finished scene lighting. To put into perspective how expensive the ray tracing is just for this very simple adjustment, it took longer to calculate these reflections than it took to do everything else we have covered in this video so far. This is because I am playing on a 1660, a GPU without ray tracing hardware, so my GPU is quite literally not built for this. If I did have a 20 series or better, it would be way faster. With all that lighting finished, it's time to draw all the transparent objects in the scene. But Acerola, I thought we were doing post-processing right now. This is AAA graphics programming. We do whatever we want, wherever we want, whenever we want. Take your sensitive ass back to Unity's built-in rendering pipeline. The transparent objects include the actual window panes themselves, these secondary drapes, and the shadows on the protagonist's face. That's right, these cool stylized shadows on the character models are fake and are actual meshes, so the artists can have absolute control over them. While you could use some sophisticated techniques like screen space shadows to get a similar look, this mesh approach is very cheap and easy and pretty common, especially in the VR chat space, as post-processing effects are too expensive for VR, so the mesh ends up having to do a lot of the heavy lifting. This is also where the graphics bug appears. The transparency on the window in the back is all messed up and noisy for some reason. After the transparent objects are drawn, we go back to post-processing. The next pass is a colorize on the protagonist, using the mask we generated earlier to do some color corrections and sharpen details, which exaggerates the borders of the shadows, making them look a bit cooler and more illustrative. The frame then finishes with anti-aliasing and some final color corrections to smooth out the crispy edges and make the room look cooler, since this scene is in the morning time. We missed the bloom because nothing in view here is bright enough apparently, but it would probably be applied on these same passes anyways, just like in Lethal Company with its final Uber post pass. Now that the game is all rendered, it's finally time for the cool user interface. No, not this UI, this UI. Despite appearances, you might think this is being drawn after the game is rendered, but it's not. It just uses the render from when the game was paused in order to not waste resources. Because of this optimization, the frame capture is only 3076 events instead of being an additional 3000 events to the previous 7600. It's very difficult to account for my own perceptual biases now, so I'm not sure if it's obvious to everyone that this is a 3D model in the background, but the frame starts with the Z prepass of the 3D model. Then its edges and lighting get drawn just like the last capture, but since there's no lights, then all of the shadow mapping and related passes get skipped and it's finished. Essentially, we swapped out the old game scene for this new scene that contains a floating model of the player. And yeah, it is the same model as the one used in game, just with different textures, and its coloring is the result of a screen space mask for the water background texture. After the new scene is finished drawing, the UI gets assembled. The two water caustic effects are rendered to separate buffers and blurred a bit. Since everything is transparent, we draw from back to front so that elements are blended on top of the previous elements. First, we draw the background image, which is the original render from when we paused, except it's posterized, meaning the values of the image were reduced to a smaller amount of values and then mapped to this dark blue to white gradient. Then the image is warped with a wave to make it look like it's being seen through water, and it's tinted heavily towards light blue. The two caustics from earlier get blended on top, and a transparent dark blue gradient is drawn to add some depth to the water. Another gradient is drawn upwards towards a lighter blue, and this cool white shape is drawn on top. Text indicating this is the main menu gets drawn, and the 3D model from earlier finally comes back. Lastly, a bunch of cool little confetti particles are blended to add some visual flair, and all the buttons are drawn. It's the same process for all the different menus in Persona 3. They are each a different pose of the same 3D model. This one is probably my favorite. But what about the battle UI? It's the same deal. Clever reuse of the same models with different shaders applied to the simple geometry to create stylized UI elements. This is a wonderful demonstration of how proper use of different camera angles and poses can make the same asset look new and interesting, rather than come off as cheap and repetitive. But what about the all-out attack finisher cards? Unfortunately, this is not God's greatest gift to stylized shaders. It is a very clever switcheroo from 3D to a drawn PNG, so out of everything, this is the only thing that is entirely artist authored. In the end, Persona 3 Reload demonstrates how the fundamentals of physically based rendering can still be used in stylized contexts, as well as how to reuse assets the right way. With this much of an improvement on the visuals of Persona 5 and the experiments with ray tracing, I'm very excited to see what Atlus has in store for Persona 6. By the way, the theme announcement for my first ever Game Jam event is going to be announced live on the channel here in a few minutes, so come check that out. Also, if you'd like to support the channel, you can help me out over on Patreon. As usual, a huge thank you to all my existing patrons. Without your support, I wouldn't be able to play Persona 3 Reload for 3 days straight while saying I'm working. That's all from me. I hope you have a great rest of your day, and I'll see you next time.